This is the Waves homework booklet, question 18. The diagram shows a ray of light incident at an angle of 60 degrees to the surface of a layer of oil that's floating on water. Always look at the diagram and relate what you've read to what you can see. Notice two values for refractive index are also given. The first step is to calculate the angle of refraction, theta, in the diagram. Here we apply Snell's law. So n1 sine theta 1 equals n2 sine theta 2. n1 refers to the refractive index of the air, which is 1, and sine theta 1 is this angle of incidence here, 60 degrees. The refractive index of the oil was 1.47, and then the second angle is labelled as theta in the diagram. Rearranging and solving, we find the angle of refraction is 36 degrees. Notice I have written here ANS. This is to direct you to use the ANS button on your calculator to hold as many significant figures as you can for your interim answer. However, when writing your solution in the exam, it makes more sense to write this number. Moving on, we're asked to calculate the critical angle for a ray of light travelling from oil to water. This equation is given on the data sheet, but you can, if you prefer, use Snell's law and work from first principles, remembering that at the critical angle of incidence, the angle of refraction is 90 degrees and sine of 90 is 1. However, if you're happy using this equation, then n2 is the second refractive index, which will always be less than the first. Total internal reflection only happens when travelling from a higher towards a lower refractive index. So that should help you to make sure you always have these numbers the right way round. Also, it's obvious that sine theta must be less than 1. So solving that, we have that the critical angle is 65 degrees. Next, we are asked to continue the path of the ray of light immediately after it strikes the boundary between the oil and the water. This is the same boundary as in the previous part of the question, so we're likely to need to consider the critical angle here. Looking back at the diagram, we see that the angle of incidence at this oil-water boundary is 36 degrees. We had calculated that previously as this angle here, which will equal this one here because they are alternate angles. If the angle of incidence is 6 degrees and the critical angle is 65, then we are less than the critical angle, so we've checked that total internal reflection will not take place. However, the light is travelling towards a lower refractive index, and so it will move faster and bend away from the normal as shown in the diagram. Part B. In the second diagram, a student has incorrectly drawn a ray of light B entering the glass and then entering the water before totally internally reflecting from the water-oil boundary. So this path is shown here. The refractive index of the glass is 1.52 and the critical angle for the glass-water boundary is about 60 degrees. We are asked to give two reasons why the ray of light B would not behave in this way and to explain our answers. I'll provide the explanation whilst referring to the diagram, and you can read the written answers at your own pace later. So starting with the beginning of the ray of light B, we're looking for anything that's incorrect. So first of all, checking the boundary from air to glass. The light is travelling towards a higher refractive index, and so it bends towards the normal. So this is correct. Next, we're travelling from glass to water, towards a lower refractive index. For this reason, we have to consider whether total internal reflection might occur. That's why we've been told the critical angle for the glass-water boundary. This is about 60 degrees. So with an angle of incidence of 40 degrees, we can rule out total internal reflection. Now we consider the refracted ray as the light passes from the glass into the water. The refractive index has reduced, and therefore this refracted ray should bend away from the normal. This is our first incorrect point that we've noticed. So we must say that the angle of refraction should be larger than the angle of incidence, because the refractive index in water is less than the refractive index in glass. We could explain that the ray of light will travel faster in the water than the glass. Considering the ray as it continues, we now study the water-oil boundary. Here we're seeing we're passing from a lower to a higher refractive index. This means that total internal reflection will not take place. So although there may be a weak reflection here, there must be a refracted ray passing on into the oil. Since we're travelling from a lower to a higher refractive index, this refracted ray would bend towards the normal. Finally, take a moment to consider how you structure your answer. We've been asked to give 2 reasons why the ray of light B would not behave in this way. So we're looking for 2 mistakes shown in the diagram and 2 explanations of why they are mistakes.